Hello, everyone. I'm Mo Yung Han. Our group is presenting the paper review, Enhancing Rating-Based Reinforcement Learning to Effectively Leverage Feedback from Large Vision Language Models. And this paper introduced the ERL-BLM method to solve the reward design bottleneck in reinforcement learning. Next. So the current reinforcement learning field has achieved a great success in several fields, but they're still using the traditional reward function, and it causes a reward design bottleneck, which is model design is slow and expensive. And next, to solve the solution is one is using the reinforcement learning from human feedback, RLFF, but this also costly and labor intensive to scale. So this paper proposal is to replace the human with an AI using a large vision language model, BLM, as a scalable procedure to judge the agent's performance. Next. So currently, there are three main approaches to automatic reward. First is the inverse reinforcement learning, learns from expert demonstration, but it is also expensive to get. And next is the learning from feedback, like RHF, which uses either the pairwise comparison, compare A vs B, or absolute evaluative rating 3 of 5 stars. And lastly, this using BLM as a direct reward signal, like with click. The paper notes this approach is often noisy and doesn't use the VRM reasoning ability. Next. So this leads to the core motivation. Most VRM feedback methods copy RLHF pairwise comparison. So why not we just use the pairwise feedback? The order argue this is flow for VRM. First is sample efficient. A better than B doesn't say how much better. Second is computationally costly, as it's double the VRM input loop. Finally, it causes a query ambiguity. If trajectories are similar, the BLM might get confused, hallucinate a preference, or say I'm unsure, which versus the data. Next. So the paper suggests is to use the absolute rating instead of the preference. The ERL BLM method queries the BLM to evaluate a single trajectory using a descriptive Likert scale, like very good or bad. Is it better because it's more expressive, it's more efficient, and it uses all the data, avoiding the unsure problem. Next. However, switching to rating introduce has two challenges. The first is data imbalance. Clearly, in training, most trajectory are very bad, while in lab, in training, most are good. So the shifting imbalance can destabilize the reward model. And the second challenge is noisy labels, which BRM are not perfect and can provide incorrect or inconsistent rating, and the system are robust to the noise. Next. Now I will pass to Sujie to introduce the solution and the methodology part of the paper.
Thank you, Yunhan, for sharing the background and the limitation of the previous models. Next, I will explain in detail the negative influence brought by these limitations and using our model method to explain how we solved these problems and achieved the better result. For the challenge one is the data imbalance. Here we visualize its influence. In the first picture, you can see the collected rating data is severely imbalanced. The bad samples is larger than the average and the good class. In the second picture, we look at the blue line. The reward obtained from the uniform training is completely unstable and may even be incorrect. In the third picture, there was a slight initial improvement, but it quickly declined. It shows the RL algorithm failed in here. Next page. So how does our model solve the challenge of data imbalance? Here we use the stratified sampling to replace of the uniform sampling, because stratified sampling ensures that each batch contains all rating categories. It avoids bad samples dominating training. We can see the example here. Okay, in the picture, the red line shows that stratified sampling leads to a much more stable and consistently improved mean reward estimation, and success rate throughout training, outperforming uniform sampling by a large margin. Okay, next page. For the challenge 2 is the noise or in-process labels. Here we use the MAE loss function to replace the cross entropy here. I will introduce the variable in the function first. The sigmoid is the one trajectory we mentioned before. The y is the true rating score assigned by the VLM. Mu here is the true label vector. The p function here, this equation maps the continuous reward values given by the reward model to probabilities for each rating level, and is used to learn the classification ability of the reward function. And here, the mu-st, it is the stratified sampling. In the previous papers have demonstrated that using MAE as the loss function is more robust in the noise environment. You can see in the picture, the green line represents the MAE function and the red line represents the cross entropy function. You can see here the green line is better than the red line. Okay, next page. Let's take an overview of the whole architecture. First, the agent collects the trajectory, and the second, the VLM model scores the trajectory segments. Third, the reward model learns a reward function based on its scores. Then, the replay buffer relabels the trajectories using this reward function, and the place function is training using this new reward for RL training, and then repeat again. Okay. I will pass to Yunhan. Hao Xian.
Oh, it's okay. Okay, thank you, Sujie. Okay, now I will analyze the ERL VLM papers experimental validation, which focuses on the datasets and results to determine the method's effectiveness. So basically, the authors demonstrated their methods across 3 domains. First is the metaver, which is a low-level continuous control. For example, sweeping an object. Second one is Alfred, which is a high-level complex language task, a language-based task. For example, a pickup an object, and most critically, a real-world saver robot to prove that it's not just a simulation success. Next, so the ERL VLM's performance was measured against 3 key baselines. First is the similarity score methods like CRIP, which are simple but often noisy. So second one is the RLVLMF, which is a crucial competitor that uses a VLM but relies on inefficient pairwise preference. And last one is the environment reward, which is the simulator's ground truth answer. Okay, next. So now for the main results of the simulation as shown in this figure 4, you can see that ERL VLM significantly outperform all the others. So CRIP-based methods, due to their volatile nature, produce noisy signals. So ERL VLM's absolute rating approach was more sample efficient than the preference-based RL VLMF. So while similar on simple tasks, RLVLMF fail in the complex Alfred environment, showing that the ERLVLM yields a better reward function with the same limited query budget. Okay, next. Surprisingly, the ERLVLM trained agent outperformed the ground truth reward agent in the Alfred environment. The sparse ground truth reward, for example, +1 after 50 steps, hindered the effective learning. So the ERL-VLM's VLM teacher automated reward shaping by assigning average ratings for partial progress, which creates a dense effective learning signal that guided the agent better than the technically correct sparse reward. So next. So the ERL-VLM was tested on a 7DOF Sawyer robot with 50 human demonstrations. As shown in this table 1, its learned reward significantly outperformed the baselines like behavior cloning and sparse reward IQL. So for the pickup banana test, the ERL VLM achieved a 47% success rate, dramatically higher than the baseline's 30% and 17%, which confirms that its practicality for physical robots. Okay, thank you.
Okay. Next is the real robot evaluations, and the experiment set ups we use the Resync Soyan 70F robot arms with the Intel RealSense cameras, and the environment is the tabletop manipulations and the setup with the RGB observations and the real-world learning from the vision large model generative the ratings without the human enables. The next is the tasks. We evaluate the three real-world tasks: the sweep board, the draw open, and the pick up bananas, which cover the pushing, the pulling, and the graphing behavior observation behaviors, and the compared method we evaluate the three baselines: the behavior cloning and IQR with sparse rewards, and the REL version large models reward model trained with the vision large model upload the ratings. And next page. So next page is about the ablations studies. The goals is to understand the how each enhancement in REL vision large model contributed to overall performance. The ERL vision large models concludes the three enhancements: the MAE loose, robust to rating noisy, and the stratified samplings, which is fixed the rating imbalance, and the weight loss, which is balance the rating densities, and we create the two ablation experiment. The first is no MAE, remove the MAE with the cross entropies, and the second is no stratified samplings, remove the stratified samplings, and weight loss, just keep the MAE only. And this is the result of our experiment. And the four ERL vision large models performs consistently best, and the result of no MAE and no stratified samplings cause clear degradations, and which confirms that each enhancement is essential. And next page. And this page is the application studies of the impact of the number of the rating classes on ERA vision large models, and we try to evaluate how varying the numbers of rating classes N2, 3, or 4 affects the performance of ERA vision large model on different robotic tasks like the sweep, into, and draw open. So this is the result of a experiment, and we can see the increasing the numbers of the classes generally degrades the performance on those texts. But interesting is the draw open performance best with the three classes, which means that the text subjectivities influence the optimal team classes. Okay, this is application studies, and next part is 进行. Thank you.
Okay, so to prove the generality of our ERL VRM method, as my teammates said before, we test it across the three completely different domains. First is in meta-word tasks, where we handle low-level continuous control tasks like sweeping a block, score a soccer. Second is in Alfred task, a high-level vision language navigation task, where the agent must follow complex natural language instruction. And the third, the most importantly, we apply this on a real-world robot. So to show exactly how the VRM works, let's look at this Alfred example, pick up the mark in the copy maker. So this is the agent first person view from time step 0 to 12. Look at the Germany analysis. As the agent navigates time step 0 to time step 10, the VRM rating is consistently bad. But look at the last two steps. When it looks down at the copy maker, the rating becomes average. When it successfully picks up the mark, the rating becomes good. This proves the VRM isn't just a judge, it's a teacher. It provides a shaping reward to guide the agent at critical moments. So how effective is the VRM feedback? We first identify a critical problem. So please look at this chart. It shows the rating distribution during training. You can clearly see that in the early stage of training, almost 100% of the rating are bad. This caused severe data imbalance. If we use this directly, the reward model will fail, leading to a training collapse. This strongly justifies why the enhancement in our paper, like stratified sampling, are absolutely essential. So finally, this figure provides the most intuitive proof of our outcome. We plot the learn reward, the blue line,
against the ground truth task progress, the dot line, along the expert trajectory. As you can see, the baseline rewards are extremely noisy and poorly aligned with the ground truth. Now look at our ERL-VRM. The signal is very smooth and highly aligned with the ground truth. This proves that ERL-VRM successfully distilled a high-quality, low-noise reward signal from the VLN. This is the fundamental reason for its superior performance. So that concludes my part. Thank you.